You're right.
All right. Morning, everybody. Hope you're doing well with your exams and stuff like that. To make your life more miserable, since it's our job, we're getting paid to do that. We actually added a project for you as well, which due next Friday. But I mean, if you see that you're struggling, we'll extend it. But I think it should be something not very complicated. So hopefully you can figure it out. Shreyas, your TA, probably most of you have met it already, but if you're not, Shreyas is the TA of this course, the master students here. So he's gonna describe a little bit about what the project is about, what you need to do. We already post things on the website, so if you go to the schedule, wherever you find the slides, you will see that I already added the description and a bare bone Python file. Shreyas will talk more about that and what needs to be done. You have a question?
The Google Docs that is due Thursday.
Yeah, sorry, next Thursday. Okay. Yeah, Thursday night, basically. Yeah. So
Can you
ready?
Yeah, can you just let me share my screen?
Oh yeah. There. Yeah.
Yeah, I just wanted to confirm the next quiz is the 13th.
It should be week 6, I think. Let me
Week 6 or 7?
Did I say 6 or 7 in the first?
7.
Okay, then it will be week 7. I'll post it on
Okay.
campus bar. Okay, are we ready?
Yeah.
All right,
Okay.
go ahead.
Cool. So if any of you guys have actually gone through the document, I also did like a small intro to Bitcoin in my last discussion, but I don't think that's necessary for the scope of this project. So the goal, at least the project is split into 2 parts. The first part of the project, you're going to be looking at building your own blockchain network, and it's very bare bones. So there's not a lot of the nitty-gritty details of how something like Bitcoin works, but the idea is to get a general understanding of how these systems actually work. So if you actually go on to the bare bones Python code, I've defined a class and given functions for each of these. So you'll realize that each of them just have a small function that you need to write. It's not that hard to do. So the first thing that you have to do is you have to initialize a Genesis block. This is the first block in your blockchain. Okay. So the first block of your blockchain is the Genesis block, which you will initialize. Okay, and then now what you're going to do is you're going to have to show, I think, 5 transactions in the blockchain. So you're going to have to show essentially 5 more blocks added to the blockchain. And each block is a transaction between parties. Okay, so if there's a transaction between party A and party B, you would, what you'd be looking, you'd have to add a block that details this transaction and then add it to the chain. Okay. And you'd also have to do what a miner does. And what a miner does is essentially perform a proof of work, which is in some sense trying to mine the block and put it onto the chain only if it's a valid block. So the details of how to do this, there's a really nice video by 3 Blue 1 Brown, which I think all of you should watch to get an idea of how this works. You can also check out the Bitcoin paper. It is quite accessible, but beware that we won't be implementing a lot of the details. Okay. So yeah, that's pretty much it in terms of what you guys have to do. Just remember that to perform anything like hashing, you can use Python libraries. And if you're doing it in language like C or C++, I'm sure there are implementations of SHA-256 because it's a fairly common protocol. So you should be able to find those online as well. So in the case where you find it becoming extremely hard, you're probably doing something wrong. Okay. The whole code, I think the one that I have is not more than 100 lines. I think you can do it even less if you choose to, like the entire thing. So it's not at all very complicated.
Yes, don't implement your own hash function as we said in the course as well, right? So first of all, it's not a secure way to do it, and then for this specific project, it's not something you need to do, right? There are standard libraries both in C, in your operating system usually. So for example, if you say something like OpenSSL, you will find it. Python library are already provided if you use Python. So yeah, it's just an API that you call for your hash function.
Yeah. I think that's pretty much all I have to say. Does anyone have any questions?
For each step, like 1,
Mhm.
2, 3, 4,
Mhm.
like is it in the file that you provide that you'll tell us how to like initialize a Genesis block? Because like I'm not sure like I understand how to do this.
How to initialize the block?
Yeah, you
for
have to watch the
example,
video first to
Yeah.
get some idea what's going on. Then take a look at the code. We provided the skeleton of the code and functions. It basically needs to, complete the functions.
Yeah.
So you need to do a little bit of reading before actually jumping into the project, and that's part of the project to learn more about blockchains at the setting. But you have all the fundamentals, so you know what is hash function, you know all those things, you know what is nonce and all those things. It just needs to understand how blockchain works, and we intentionally did it this way so you actually go and watch those videos.
okay, thank you.
Okay. And the second part of the project is sort of in some sense a sanity check to check if you did the video first part correct. So let me just show you guys one. So this should be the screen you see if you go onto that website over there. And so what you're supposed to do is the sheet that you see over there is a blockchain that we have right now, and that's ours. Okay. So that is the ECE 188 blockchain, and you'd see that my name is there. I was a Genesis block, and then Professor Serpak is also there. So your goal is to put your name onto that chain. Okay. And the way that works is fairly simple.
Board of Glory.
You would enter your name here. So for example, Elon. And then with the hash value with the previous hash value that you have, this is what you would do in your proof of work. In your proof of work, you realize that you would use the previous hash value, that's the hash value of the previous block, your name or the data that you want to send. In this case, it's your name, and a nonce, okay? So essentially what you're trying to do is write a small script that will figure out what that nonce is, that solves a cryptographic puzzle, okay? And in this case, you realize that the cryptographic puzzle is that you just have to generate a hash that starts with 4 zeros. Okay, does that make sense? So over here, if I were just to enter Elon and 10, it's not going to work, okay? Because 10 is not the nonce that's also, okay? But if I use Elon and 78256, you got mined onto the chain. Okay. So now if you were to reload the page, and you would see Elon added to the chain. Okay. So yeah. Questions?
So if we initialize the Genesis block on our machine, we're gonna have a different blockchain than your.
Oh yeah, yeah. This is separate. The goal of this is just to add your data onto my block.
Okay,
So
it's part 2.
exactly. So in this part, you're the miner.
Okay.
So your goal is on my blockchain, someone is trying to make a transaction, and you're the miner who's mining it onto the chain.
Wait, sorry, do you mind saying again, like how you got that?
How I got that one on top?
No,
Or
no, the
the
one that you
nonce?
entered, yeah.
Oh yeah. So that's what you guys have to do. The goal is to find out how to
No,
find
no,
that.
like I meant, like, why did you say that? Like, I was confused, like you said about like, it has to start with 4 zeros.
Oh yeah.
Yeah,
So when the goal of the miner in the whole blockchain system is to add blocks onto the chain, onto the blockchain, right? So the way that a miner has to do it has to be completely in terms of brute force, because the miner gets money if he makes a transaction.
Yeah.
So if a miner finds an algorithm to actually do this, then it's not fair, because then he just abuse the algorithm and just mine blocks. So the goal is to make that problem only possible through brute force and NP-hard. So this is a 64-bit hex hash, and for our purposes, the cryptographic puzzle is that the hash that you generate has to start with 4 zeros. But for I think for Bitcoin, it's something like 10 zeros, which is much harder to do. And
So it's not any hash, you have to find specific hash. And you are in a hash space of maybe 2 to the power of 64. So you have to search this space to find this specific, so this specific nonce that results into this specific hash, right? And in order to make it a blockchain, we start with 0, 0, then 0, 1, 0, 2, so on and so forth.
So we're using the proof of work function to find the noise.
A part of the proof of work.
I also have a question, are we allowed to change any like the structure of the variables?
Yeah, you can do anything with
Structure of the what? Sorry.
the
Like,
bare bones.
the variables.
Oh, yeah,
Yeah,
yeah.
you don't even need to
You
use
don't
the
even
bare
need to
bones
use it.
code.
Yeah, yeah.
You can use anything else you want. We just gave it to you to give you to help you. But if you just want to throw it away and use your own code, that's fine.
Wait, so for part one, would the transaction just be like person A says person B like $2?
Yeah.
So it's just straight up.
Yeah.
Should our script submit the nonce for us, or is it just supposed to generate nonce and we submit it manually?
You can just generate the nonce Sunday manually. In fact, if you guys cannot generate a script that will, because I don't want it to keep submitting values, because I'm not sure how the backend is gonna handle that. So, and I can check for spam, so if you guys decide to be mean and spam the Excel file, I really
Yeah,
can't.
you can spam the system file if you want to. In that case, then we need to make the puzzle harder so that they cannot do
Yeah.
it, but. And by the way, you can put anything you want in that name section. You don't have to put your name, if anything else. Just something that is distinguishable, because when you're submitting a report, just show that this is the block that you added. So if you don't want to put your name or whatever else, that's fine.
So is that hash going to change at the top since now you
Yes.
like?
Yes. So the hash for that is now the hash for this one, right here.
Right.
For Elon. Yeah, so the hash keeps changing. So
Yeah.
just keep in mind that whenever you're doing this, you would essentially just need 3 values. You would need the hash, you'd need your name, and you'd need the nonce. And just these 3 values should produce, or think of writing this function that given your name, hash, and the nonce, it should say yes or no to check if it's the right answer. So I would recommend doing this bit first, because it gives you an idea of how proof of work works, and then you can build your own blockchain easily. Anything else?
Are we good? And then you can always, post things on Campus Wire and come to our office hours.
Office hours,
Or ask
email.
questions during the class as well.
Or you can come to my discussion.
All right? Yeah, or come to the discussion. All right,
Thank
thank
you.
you, guys. Yeah, see you later. Okay. So to make your life a little bit easier, good news is that I'm asking you to do 1 paper review per week instead of 2 from this week, okay? So you don't have to review 2 papers, just do 1, okay? So then kind of balance with your projects and all the other things. Any other questions?
For this week.
No, generally for now, unless I tell you to go back to.
Will the papers be covered on our quizzes?
So as I said, the paper itself won't be, because not everybody has read it. But things that we're gonna discuss during the lecture, including the presentation, will be. But again, we are not assuming that you have read the paper, so the questions that we're gonna ask will be mainly high-level questions. But you also got the questions, right? It's mostly true, false, kind of like short answer kind of questions. Any other questions? What's that? Next Thursday. Okay, so let me quickly go over the remaining part of memory safety and then we start the paper presentations. So we said that memory safety, generally the goal is hijacking the control flow or modifying some codes and values, right? So either of these two, And then we kind of extensively talked about how do we do the control flow integrity attacks. Mainly, we talked about buffer overflow. And we said that essentially the way it works is that you have some sort of a buffer that takes usually the value from the input. And the adversary basically can use this bug that we are assuming that there is a specific size for the buffer, but the adversary actually doesn't follow that assumption, and instead sending much larger input data. And as a result, what will happen is that not only we're going to fill this part of the memory, the stack, but the overflow of that information will start overwriting things. And we said that the stack, things gonna grow on the up direction for this specific example. So as a result, all these other things that are before the buffer are gonna be also overwritten, including the base pointer, the parameters, and all those things. But the most important thing is actually this return address gonna be also overwritten. And what will happen is that, when we're gonna overwrite this part, we can basically write our own address here, and the function that they're executing this function has no idea that this return address has been overwritten. So it reads to the return instruction and wants to return back to the main, thinking that, okay, this address was a valid address and we have to go back to that address. But basically what will happen in reality is that the code will jump into this address here, and this address is actually the beginning of the malicious code. I think there was some confusion of why we are doing it, upwards and now downwards. I posted on campus. Where did you read? Did you get the idea? Yeah. So generally, the idea is that first of all, two things. One is so when they build the way that the stack grows, they didn't think about buffer overflow, unfortunately. So that's how they structure it. And afterwards, and this is mainly for x86 machines. And afterwards, what happened is you always wanted to have backward compatibility because of the compiler and the operating system and so on. So you always do, even though they knew that there is a buffer overflow potential vulnerability, the cost of changing things to grow in the other opposite direction was really huge, right? So they basically didn't change it. Plus, what will happen is that if if your buffer grows in this direction, yeah, of course you wouldn't, override this return address, but typically you have lots of other things, as I said last time. You have a bunch of other things down the stack as well, and those things are going to be overwritten. And usually what happens is that you very likely you're going to have another function here. So you probably have another return address somewhere here. So that would be overwritten as a result of you're growing the buffer in this direction. So that doesn't completely solve the problem. And this combined with the fact that changing things in hardware would be very costly results in the fact that we never do it this direction as well, because that doesn't really solve the problem. Yeah. Go.
Why can't the computer just cut off the input at 20 bits?
But how do you know you get 20 bits? Well, you have to check it, right?
Yeah.
So yeah, so there are some functions, unfortunately, that doesn't do the check. So you have to actually manually check it yourself. So when you're writing the code, you have to do that manual check. And oftentimes it's possible that you don't do it. So it's basically a bug. It's not something that it's fundamental. It's a bug that you have to be careful. There are languages that are safe, and that's exactly what they do. That they don't allow you to overwrite the buffer, and that's why those safe languages are very popular and powerful. But unfortunately, something like C or C++ language is not a safe language, and that's the main reason. And then unfortunately, kernels of operating systems are written in C. There are lots of very critical applications that's been written in C, and all of them are vulnerable to buffer. Okay. So we kind of talked about the jumping to somewhere else in the code, and then we also talked about, okay, what should we do when we are jumping? Because jumping is one part of the problem for the adversary. The second part is, oh shit. So now we have to control, then what, right? And we talked about the notion of the concept of shell code, and we essentially said that shell code is this very tiny piece of code that invokes a shell. And then when you invoke a shell, then you virtually have full control of the system. Then you can do whatever you want with the system. So this kind of like becomes the algorithm for doing this. So you need to find the vulnerability first. You need to find the address that you want to overwrite. You need to somehow inject your shell code or whatever malicious code that you have into the memory. You have to jump to that point, and after that, you have full control of the system. You can do whatever you want basically. All right. One additional problem was that, okay, now we can jump and now we know what to do, but the other question is how to inject that. And one of the interesting things that can be done is that given that we can actually inject, override the buffer, why don't we actually inject our code with it, right? So instead of like overwriting the buffer with junks and some return address, what can we do is that this is the return address that's going to be the overwritten, but as a part of the overwriting, we're going to also inject our shell code here as well. And shell code, as I said, it's very tiny piece of code. It's basically just calling a specific system call. So it's only a few lines of code. So a few bytes would be satisfactory for the shell code. And as a result, what we do, we usually add this additional buffer lane, or what we call landing zone. Oops. Uh-oh. See if it works. Yeah. Any pen that you can borrow me?
You can grab it from my iPad.
Okay.
I have extra pen tips if you.
No, I think it's broken.
You can't turn it in.
So?
You can't turn it in.
No, I think it's. No, it's broken from inside. So it's kind of like the tip is not fully out. So it's just broken some part of it.
Oh, it happened to
Yeah,
me
yeah.
once.
So do you have an extra pen, someone?
Yeah,
Yeah, it should be under.
Oh. Was it? Okay. I promise not to break this. So yeah, we're gonna have this landing area, which basically is just a bunch of no-op instructions. So what we're gonna do is that we're gonna jump to this address here, somewhere in here, and since these are all no-ops, nothing bad will happen. We're gonna just execute a bunch of no-ops, and we're gonna eventually start running the shell. All right, so this increases the chance of a successful attacks for these first. Okay, so that's kind of it for what the attack was, and this is mainly what we covered last lecture. Now let's talk about the defense mechanisms. Any questions so far? Yeah.
Can you explain no-op again? Like the attackers jump into a bunch of no-ops first before they execute their mission?
Yeah. So the idea is this, that the alternative of this was we have the return address and then we have our shell code, right? And then this return address, we override the return address, right? So we have to jump to the beginning of this shell code, right? In order to be able to execute the shell.
The shell code, like this thing that you're running.
You're injecting, right? Yeah. Yeah. So you kind of like inject this and inject all of these. Let's say this is like 8 bytes. Okay. So what you need to do is know exactly where this is, right? So you need the exact address of this in your stack so that you jump exactly to the same bytes. So if you are off by 1 byte, you are executing maybe here, and then your shell code won't work, right? So this is actually for some for some reason this is not simple to do that we're not going to talk about. So as a result, what you can do is that saying that okay, instead of like find this exact address, what we can do is that maybe I'm adding this additional kind of no-op instructions, these instructions that we don't really care.
To the shell.
to the shellcode, so that instead of finding this place, anywhere here will do.
Okay.
Alright, so basically I'm jumping anywhere here, I start executing some no-ops, which is kind of like, neutral instructions. Excuse me. And afterwards, eventually I'm gonna reach to the top of my shellcode and then I can safely execute this question. Okay?
But would it be still possible to jump by mistake to the middle of the shell code instead of the landing area?
So you have to be conservative and try to, add a little bit more. So when you're making your guess, you make a conservative guess in the opposite direction. Okay? So you think that your address would be, I don't know, address. So what you can do is like adding some sort of a guard, which is plus some X. And that kind of gives you the idea. But you have to be still fairly accurate, but this increases your chances of that. Okay? All right, so let's talk about defense. So the first thing that you can do is what's called stack canaries. Kind of like we briefly talked about this. So essentially, since if I go up here, so if you see here, basically, since your stack kind of look like this, that there is a return address here, and then there is a buffer. So there is usually something in between these two. What you can do is that here you can add an additional entry, which we call canary. And this canary will always sit between your buffer and your return address. And if you want to, do the buffer overflow, what should happen in order to overwrite this, we need to overwrite this part as well. This is just the way that the stack works, right? So if you want to overwrite the return address, along the way, we need to overwrite the stack canary, the canary value as well, all right? So the simple thing that we can do is that when we want to jump to the return address, when we want to jump back, we first go and check this canary value and see if this is the value that it's supposed to be. This is the old value that we were expecting. And if that's the case, then it means that this part has not been overwritten, right? And then it's safe to jump. If this part has been overwritten, then we shouldn't jump, right? And this way kind of we detect that there is a possible buffer overflow attack. So we don't prevent the buffer overflow, but at least we detect that there is a potential buffer overflow. So there are some mechanics, including like what value should be used for the canary, how do we remember those values and all those things. If you're more interested on this, you have to read more about it. But generally, the compiler is the one that generate these canary values with some specific algorithms. This could be either some sort of a counter or could be some random value that is being generated. Okay. So that's kind of the idea of the canaries. Any questions here?
Can the attacker give a fake canary which just accidentally matched? So
Yes. Actually, well, later on, I'm going to talk about this attack defense cycle. And you will see it's not that hard for the attacker to find that canary value anyway. So once they overwrite the buffer, they replace the canary value with the fake canary value, which actually matching the original canary value, and then they overwrite the return. The second thing that can be done is what's called the data execution prevention, or DEP. So if you remember, I said that basically what the attacker can do is injecting the shellcode as part of the stack as well, right? So what we can do is making sure that the stack is what's called non-executable, or at least part of the stack is non-executable. And what would this do is that the stack can only be used for storing and loading data, and not for executing code. So if your PC, remember the way that the executing code was addressing the PC to that specific address, right? So what the operating system can do is that knowing that, okay, there is this portion of the memory, maybe addresses that start with X and ends with Y. These part of the addresses, if PC jumps to those addresses, we're gonna throw an error and we're not gonna execute those instructions, okay? Because that part is kind of like data only parts. They're non-executable, all right? So as a result, even if the attacker injects the code into the stack, then they cannot execute it because it's stack generally by default is non-executable. And that can save a lot of, can eliminate a lot of attacks because generally that's kind of like, put the part of the stack out of commission. Okay, does it make sense? Any questions? So this is actually has obviously some disadvantages. One of the disadvantages is the inconvenience that it brings, because you sometimes actually do want to be able to run things on your stack, and that's not the adversary. That's actually a legitimate user that for some reason wants to inject something and start executing that. So when we are kind of do this preventive methodologies and this kind of limitations, add this limitations to the system. Of course, it makes us more secure, but unfortunately, it also comes with costs of either the performance hit or some sort of, reducing or limiting some sort of features that you generally want your system to have. Okay, so that's the problem with that. But generally, these days, all the modern systems do use this feature in their operating system. The third option is what's called ASLR, address space layout randomization. So remember I said to you that, we have like data block, we have code block, we have heap, we have stack and all those things. And it's kind of like, something that statically we are kind of like creating. What we can do is basically mix and match and move these things around for each different process. And from each different execution. So we don't need to actually keep the same blocks or position for each block. All we need to do is kind of like knowing where the beginning of this is, and the operating system is kind of like move these things around. And the benefit of this is that then remember I said that the attacker needs to know where the return address should be for their code. Once I move these things around, then the attacker no longer knows what exactly their code is stored, right? And as a result, although the attacker can still do the buffer overflow, they cannot jump to a valid position of their malicious code. So at least the return would be returned to some junk and nothing bad will happen. So it's kind of like you kind of try to launch the attack, but the actual payload never executes because you think that your code is stored somewhere in your memory, but since you actually move things around into your memory, that never actually happens. Okay, so ASLR is again something that's been extensively used in almost all the modern operating system, and this is typically when you restart or reboot your system, it starts moving things around. And since we do the address translation, this moving things around is not that difficult to achieve because essentially all you need to do is changing things in your page table. Does that make sense?
On the previous slide, the data execution you mentioned, did you say that's the same thing as making the stack non-executable?
Yes.
Oh.
So not just stack, think about the entire memory, because stack is just nothing but part of the memory. So you can always restrict part of your memory as non-executable.
You can make the entire memory read-only.
Not read-only, still you can write, but you cannot execute. So there are three things that you can do with your memory: read, write, and execute. So you don't allow your PC to get that value. You still can change that value to whatever you want, but you don't allow your PC to run things from there.
So like you're saying like memory between 0, 0, and 0 is 200.
Yeah.
You make sure that like the operating system restricts your PC from being anywhere between 0 to 200.
Yeah, exactly. So like, let's say this is the the preventive part. So if the operating system sees that your PC is going to be somewhere in here, it's gonna block it.
Okay.
It's kind of like per page basically. So when you do the address translation, remember I said that there are some flags that we check to do the translation. What's that?
In the virtual address?
Yeah. So from virtual to physical, we need to go to the page table. So we get the physical address. But in addition to the physical address, I said that basically you have different indices, which are the virtual address. Within this, each of these, there is an entry, which is the physical address. But there's also typically multiple different flags. And these flags is actually, one of the flags is actually exactly this, that whether this page is executable or not executable.
Oh.
just one bit. So let's say 0 means non-executable and 1 means executable.
And then how does the operating system like prevent the PC from getting one of those values? Like what if it realizes that it's non-executable, like that bit is, let's say it says 0 meaning it's non-executable, and it realizes the PC is kind of going to that value, like what is it?
So it's gonna throw an error, exception usually or trap. So like things like segmentation fault that you see in your system, that's one of the reasons. So you throw some exception, saying that, oh, there's this error number 497 or something like that.
Okay.
So that really depends on how you implement your operating system, but typically this results in some sort of exception.
Okay, no, it's like my question was like, does it just automatically jump to the memory after that or before that and continue screen, or is it just like completely stopping?
So you have to understand how the exception works generally. So exception is nothing but, again, a list of pointer to some functions. So function 1, function 2, and so on and so forth. So what will happen is that the operating system sees the address translation request. It has to go to that page table. It sees that, oh, this is actually non-executable. So instead of actually giving the physical address to that process, it's going to go and jump to this beginning of this function, which is just list of function pointers. And these are different executions. These are different exceptions. When we jump to that point, then depending on which exception it is, we're going to jump into that function. And that function is what's called the exception handler. So for example, if there is a specific handler for this type of exceptions, we need to do that and so on. But generally, for your point of view, what will happen is that your operating system prevents the system to normally operate. So it's going to stop that, do something else, like something emerges. To know what exactly that is, you have to go through the operating system and the actual implementation.
How do we determine which parts that we make non-executable?
So generally, that's again when we're creating the process for creating, we are allocating memory to each process. The operating system takes care of that. So, for example, rule of thumb is usually makes the stack non-executable. So when the operating system allocates memory for stack for this specific process, it automatically put that into their to the non-executable.
So those parts keep changing, like as we.
Yes. And then this, in addition to ASLR, is actually to make things even more random, because you want to also move things around. So part of the memory that is, not executable is actually might be actually keep changing.
So what this does is it keeps calculating like the new facts. Keeps updating,
Keep calculating what?
like new facts.
Kind of, yes. So it's more of a range usually, so it doesn't need to go through every single page table. So it's mostly like, within from this range to this range. So to things makes much more faster and more performance, they usually like go with like to the power of something range to make it easier. So it's kind of like works as blocks rather than pages. All right. So this is the ASLR. By the way, all of these can be broken, as I'm going to talk about. And then the final thing is what's called control flow integrity. Yeah.
Is the ASLR happening in physical space or virtual space?
So no, physical is usually at the virtual space. So at the translation space, basically. So you don't need to physically move things around. You just need to change the map, right? So the last thing is CFI, or control flow integrity. So basically what the CFI says is at the end of the day, you're basically calling a bunch of functions from each other, right? Functions within functions, then you return, and go back, right? So what you can do is kind of like profile your application to know that what is exactly these control flow transfer. Like, what are the legit control flow transfer? From function A, I can jump to function B or C or D maybe. From B, I can jump to C and so on and so forth. And I need to kind of like have a profiling phase where I see all these possible jumps and transfer from one control flow parts to another control flow. And what I would do is then just keep track and remember all these possible and valid transitions. And during the execution, then whenever this jump happens, I'll go and see whether this is a legitimate jump or whether it's not a legitimate jump, right? So basically, whenever I see a return and I see that, for example, from function C, I'm returning to function B, I go back and see in my profiling phase, have I ever seen that C jumps back to B or not, okay? And if I've seen it before during the training phase, which was the safe period that we execute this, then this means that we have to allow this and this can, move forward. If we haven't seen that and see that, oh, C jumps to this part of the memory that I've never seen, or C jumps to A that we haven't seen before, then again, we raise a flag and we stop the program from executing further. All right. The same situation as the other ideas that I just showed. So basically, you enforce all these specific transitions from here to there, from there to somewhere else. And in order to understand what are the possible transitions, you need to actually run the code multiple times with different inputs in order to know what are those possible. It's might be impossible to see all the possible transitions, and that's kind of like what's the fundamental limitation with CFIA. But it's kind of fairly accurate in most cases because you can kind of see all the possible transitions if you want to.
Can you figure out what all the possible like jumps, the control flow transfers are just by looking at the different jump and call instructions?
Yeah, you can, but the problem is sometimes your jumps are indirect jumps, right? So for example, if your value is 1, you jump to this address. If 2, you jump to another address. 3 to another address, and so on. So if you jump to a specific value, then you cannot know it statically. You need to only do it dynamically. But regular jumps that jumps to a specific address, static address, yes, you know it even before executing.
Where is this design? Is it designing hardware?
Yeah, you can either, you usually design it as a separate part, or you can design it as part of the operating system. But typically, hardware is the ones that enforce this. Other question?
So profiling happens is that something that happens at runtime, or when does that occur?
So usually profiling should happen before that you actually deploy your system. So the profiling has to happen at the safe location, a safe situation. So for example, the developer of the software creates the software. They also runs the profiling phase. They have all these possible control flow transfer. And when they, for example, deploy the actual software, they deploy this profiling information or training phase information. Okay. All right. So this is kind of like, there are also other methods for defending against control flow attacks, given that it's a very important topic. But unfortunately, what happens is that all of these things, even though they sound very reasonable and they indeed actually reduce the chances of buffer overflow, unfortunately, all of them have been broken. For example, for stack canary, there are papers that have shown that, you can actually find a canary, you can replace the canary with something else, you can fool the system to think that it's actually, reading the same canary and so on. For depth, you can actually jump into other part of the program that is actually, because eventually you need some part of your memory that is executable. Also, what you can do is that maybe shifting your code such a way that actually fits into that part of the memory. For ASLR, people have shown that part of the, the memory, memory block can be actually found. And if you find that, the rest can be kind of guessed. So again, this is very sophisticated attack, but generally what happens is that you can kind of also guess where this randomization is and what happens to the randomization. But generally, it's not important to know exactly how those attacks works. If you're interested, you can take a look at them. But the idea is that this is unfortunately the cycle between the attacker and defenders. And you come up with an idea such as control flow integrity or depth, but the attacker also becomes smarter and come up with an idea to even circumvent that. So these days, attacks are so sophisticated that's kind of jump over multiple of these hurdles, right? So it jumps over ASLR, jumps over DApp, jumps over control flow integrity, and so on and so on. All right, so that's kind of like where we are at, right now. There is no final, solution for it, and this story continues as we move forward. Okay. Any other question? So let me quickly go over the last thing before we start the paper presentations, and that's what's called return-oriented programming. So the ROP attacks or return-oriented programming is this more extra sophisticated attacks that basically say that, oh, we don't even need to inject something into your code. What we can do is reusing the code already existed into the memory. All right. So what we can do is basically, if we, for example, wants to invoke a shell, remember I told you that invoking a shell was nothing but, calling a specific function, system call. So what people have found is that this call of system call is actually already existed into standard libraries like Lexi. So all you need to do is basically calling that function with specific variables that you need. So calling the system call with your specific code that you want. And this libc is already existed into the memory because all the modern systems do have standard libraries such as this. So what will happen is basically when you are doing your buffer overflow attack, you don't inject anything to your code. All you need to do is jumping into this system call, and the only thing you need to add is some variables that you need to call that function, and you put it here somewhere. And this way you kind of like jump into that with these variables, and then that will create invoking a shell. There is some minor details about how exactly we do it. We don't have time to go over it, but it's very interesting and very cool attack. So if you're interested, you actually go and see how ROP works. There are lots and lots of tutorials for it. There are lots of videos for it, so you can watch it if you're interested. But generally, the idea is that we don't even inject one single line of code into our system. We just reuse the codes that existed into systems, and people actually these days shown that you can do anything you want with the system. This is actually Turing complete, this attacks, which means that you can basically run any arbitrary algorithm by just finding the gadgets into the memory. Okay. Any final questions? All right, and then there's also all sorts of other attacks in addition to buffer overflow. So there's things like keep spraying, use after free, and all those things. The goal of this lecture was like just getting you familiar with this concept, but generally all of them are kind of using some sort of vulnerability that I just described in order to jump to some part of the memory that it wasn't supposed to. All right, so basically hijacking the control flow, start executing the malicious code, and then executing some payload that we discussed before about okay, you can do this and that. Okay. So yeah, this is kind of like if you want to have a big picture of potential attacks, this is actually a very nice figure that's kind of like talk about all the possibilities, so like modifying code, modifying data, modifying pointer, and all those things. This is actually from this paper here. So if you're interested, this is actually quite heavy paper. Very nicely talk about all these possible attacks. So if you're interested, go and take a look. It's an optional video. Okay. All right. So that's it for memory safety. Let's now move on to the paper presentation. Any final question about memory safety? Okay. So who is the first person to who's presenting first? I'll bring the factor. Let's have a quick, maybe 2-3 minutes break before we start. All right, guys, let's go. Okay. Guys, let's get started.
Morning, everyone. I'm Jackson, and
I'm Rahul.
we are going to talk about Thunderbolt, the software-based fault injection attacks against Intel SGX.
Somebody else.
So what is the problem with Thunderbolt? So the problem is that the security of modern systems is built on abstractions of the hardware, and the goal of these processor developers is to optimize efficiency and performance requirements. So that's always what they're going to try to do. And the catch is that modern processors cannot run at their maximum clock frequency, because as you increase the clock frequency of processors, it takes increasingly more amounts of power. And if you use increasingly more amounts of power, then you can run into issues like overheating data centers, which is obviously bad. So the goal of processor designers in current generations is to try to keep the clock frequency and supply voltage as low as possible. But they're obviously still trying to optimize to meet efficiency and performance requirements. So they're trying to do both things at the same time. They're trying to keep the clock frequency and supply voltage low while keeping up their optimizations. And the decreasing supply voltage in new generations of DRAM, because obviously processor designers are trying to keep supply voltage as low as possible. That's actually leading to smaller charges in the capacitors storing the single bits of information. So what's actually happening is the Roehamer effect, and that's where single bits of memory in the DRAM are interacting with each other, and they're actually changing nearby rows of memory in the DRAM. And that's obviously very bad because attackers can take advantage of that. So the Roehamer effect can be exploited to arrange practical attacks for privilege escalation. And then they can inject faults in cryptographic primitives or read inaccessible memory locations. And then there's a cool diagram at the bottom here showing that basically the attackers are doing undervolting by writing to MSR registers, which is multiple registers. And then that's obviously manipulating voltage and then causing failure with Intel SGX.
So just a quick background. This is based off of another course of 115C. It's like when you have MOSFET circuits, there's timing characteristics, and the basic background, bits are either 0 or 1, and if it's in between, like there's like a little threshold where if it's above, it's a 1, but if in between, it's like you don't know what it is. So that happens because you read at the wrong time, or because it's the voltage isn't climbing fast enough. So if you look over there, you see that there's the voltage 1, voltage 2, voltage 3. As you go down, the threshold doesn't decrease properly with it sometimes. So then if you read too early, you'll get like an indeterminate voltage. And that means that you don't know what it is. So this is also determined by your voltage and frequency. So basically, that's like treat like an RC curve. If you remember basic physics and electronic circuits, treat like RC curve, right? So if you read too quickly every single time, you will get this time where it's like it hasn't charged fully, and therefore you don't even know what it is. So this is like your 0, which is a fast scroll, and you get your 1 over there, which is meerkat, right? And if you read it too quickly, and as it's transforming, you get this indeterminate animal in the middle, right? So this is even more background, right? So this is more background on SGX. So you get your voltage controller moves off chip after it has one Broadwell. So this is basically only Intel x86, right? So it has one Broadwell. They actually had the power on the chip, like they had it actually built in. They didn't like contact the motherboard. But now with the newer chips, they're like, we're going to move it off to the motherboard, and then the VID, which is the voltage ID, gets sent to the motherboard, and the motherboard determines the voltage. So that means the voltage is controlled by the register, which is open to OS, which in our threat model is not trusted. And here we have a wonderful example of what 0.1 volts can do.
So Volspin is the OS in this case, right? It's the malicious version.
Yeah,
right?
the malicious. Yeah.
So let's talk about the proposed contributions. So obviously a main contribution of the paper is finding this new attack surface in Intel SGX, which they called Thunderbolt. It's a novel software-based fault attack on Intel processors. And the kind of new thing with Thunderbolt is that it can bypass Intel SGX's integrity guarantees. So basically, it can attack the processor package by switching on the attack surface of undervolting. And there obviously might be many more attack surfaces that could be found, but that's the main one that's discussed in this paper. And another contribution of the paper is that they showed how dangerous the Thunderbolt attacks can be by attacking Intel's RSA, CRT, and AES implementation. So they basically took down Intel's encryption algorithms using Thunderbolt attacks. And then they can obviously reconstruct cryptographic keys, which we learned is really bad. This should not be visible to attackers. And then they explored the use of Thunderbolt by using safety errors into enclave code, which should be trusted and protected. But obviously, the Thunderbolt attackers can use undervolting to write to MSR registers, and then that can obviously lead to getting into this enclave code. And then what they basically do is redirect enclave pointers into untrusted memory. So they get access to memory that they shouldn't have access to. And then they can also cause heap overflows in SGX runtimes. And the paper also talks about countermeasures to Thunderbolt, but the main chunk of the paper focuses on the problem of Thunderbolt itself because they haven't really identified any solutions to stopping these attacks. And they talk about an Intel mitigation plan that was developed to stop Thunderbolt attacks, but they talk about how it's problematic because there are still certain power and clock features of Intel SGX systems that attackers can still manipulate to get around Intel's mitigation plan. Yeah, this is a picture of Thunderbolt attacks.
So there are several evaluation methods, and well, actually, there's only one evaluation method, but there's multiple ways to get it. So the evaluation method is how well can you produce erroneous behavior? How well can you make it so that it messes up every single time? Or predictably mess up. So for example, fault injection, specifically using multiplication. They found out that if you have it in a specific direction, like let's say your first bit is much larger than your second, or your first multiplicand is larger than your second multiple, like it's more likely to cause an error. And then since multiplication is used in like so many different functions, it can cause a lot of predictable errors, and then this can also give you a lot of like ways you can manipulate the data. So this also allows you to go and mess around with AES. Specifically, you can change several stages, and then as you change each stage, the next stage will be more wrong in a way. And then there's also key extraction, where specifically if you feed it incorrect information and you get incorrect information, you can find out the original key. And then enclave exploitation is similar to what we just talked about in class. It's you're using the multiplication to get outside of the enclave. And here we have a very nice cat. Hi cat. Yeah, thank you.
Oh, nice. More important.
So now let's talk about some of the results of the paper. So one of the main results of the paper is that countermeasures cannot be implemented at the level of untrusted OS or in the untrusted runtime components, because privileged adversaries can manipulate MSR 0x150, which is one of the model-specific registers that attackers can write to do undervolting, and they can basically fault in enclave computation. So this is kind of a cool picture showing that an attacker can do undervolting in CPU registers, and then that's voltage manipulation. And then they can gain direct access to the enclave, which is obviously bad. So then some of the measures that you can use to mitigate undervolt are preventing unsafe undervolting directly at the level of CPU hardware and microcode. So you can sort of like develop measures to prevent any voltage manipulation in your MSR registers, but the paper talks about how that specific method hasn't really been fleshed out that much because there haven't been any mitigation plans developed by anyone, even including Intel, that can realistically achieve that. And another measure that they talk about is hardening the trusted in-enclave code itself against faults. So that would basically be making measures to make it hard to redirect any pointers in the enclave code, basically doing any protection specific to the enclave itself. And then the paper talks extensively about how Intel's mitigation plan doesn't cover the root cause for Thunderbolt. So Intel basically looked at these Thunderbolt attacks and developed their own plan to try to stop it. But basically, their plan revolved around protections against the MSR registers to try to stop Thunderbolting. But the writers of the paper found that you can still do manipulations with memory and the power and clock features of Intel SGX to get into the system anyway. So a lot more work still needs to be done by designers of these mitigation plans to make them more robust. And then the paper also notes that undervolting is not the only attack surface of Intel SGX that has been newly discovered, that there might be more in the future, more attack surfaces found. So the developers of Intel's mitigation plan need to take those into account as well. So they don't only need to worry about undervolting.
So the potential future work agrees with what is what holds the stack, right? So there's a lot of other implementations that allow undervolting, but not with the BIOS mechanism. So like there's ways to do it that don't involve what Intel did. So what Intel did was they mainly simply said, hey, you can't undervolt. And then all the companies agreed with it and says, okay, we're gonna push a new BIOS update. I won't let you undervolt your CPU, right? And then so this is done, that was the solution, just BIOS and microcurrent, right? But then there are several undervolting advantages, such as like energy saving, reduced thermals, and efficiency. So there's like a few problems with several laptops that have like poor cooling, right? They have like, there's always thermal throttling. And that's a problem that you could evade with undervolting. So this is more applicable to the laptop market. Most of the time SGX isn't for your laptop, but they specifically pushed the whole BIOS update to like a bunch of laptops and a bunch of like portable devices for some reason. So yeah, problems now sometimes. Occasionally, depending on your laptop model, it has to be like after 2015 to like around now. So there's also an introduction of E cores and P cores, right? So there's like efficiency and performance cores in Intel's most recent line. It's the 12th gen. So this is pretty much able to do work efficiently, like power efficiently, and then if you want to like do performance, it also does performance as well. So it separates them out. And then since that sometimes the E core and the P core they run at different voltages, they're separated for server workload. So like if you want to do like Intel SGX, you'll have like two separate actual like dies. And then the most recent way I actually found a paper that solved Thunderbolt with software level. So pretty much what it did was it inserted several lines that would, and then it'll check basically the voltage at each line. But then like the one problem that it did run into was that it did slow down the overall process by like around 20%. So, and other main picture. Yeah. So my discussion portion was researchers kept the frequency constant for HCP during this experiment. Technically, a higher frequency can also cause errors in system instability. So my example would be clock screw, which was actually it was also mentioned in the paper, and it's mainly they changed the clock speed so that they could go cause errors and system instability. So why during this specific example for x86 did they not use frequency? And like overclock it and then keep the voltage. Let's think about it.
And then another discussion point would be that Intel's mitigation plan was found to be imperfect because they didn't consider injections through power and clock management features. So something to think about would be what research would Intel need to do in the future to consider that attackers can still manipulate systems based on these power and clock management features, and how can they use some of those details to develop a more robust mitigation plan against Thunderbolt attacks and other similar attacks onto Intel SGX. And then another discussion point would be attackers can abuse voltage scaling, which is pretty much what was the attack surface talked about in this paper.
So they can abuse voltage scaling to corrupt SGX enclave computations. And then something to think about is what other possible attack surfaces might there be in Intel SGX that attackers could use in the future, that maybe in the future Intel does develop a mitigation plan. Like, for example, what if they do find a way to stop undervolting? Then attackers are obviously going to create new attack surfaces in Intel SGX. So you could think about what some of those attack surfaces could be.
All right, thank you so much. Any questions? Next group, so you guys can stay if there's any questions, but other groups, next group can actually come over here too.
I sent you an email to share it.
Yeah,
Email should have gone to share. I'm supposed to.
Yeah, we can, yeah. You can actually like kind of put it like this so that it actually captures both of you.
Oh, we just turn it.
There you go. Okay. Where is my? Okay. Yeah, so just before jumping into this, generally this features that been added to processors is just for increasing the efficiency of the system. So for example, Intel thought that, oh, what if we actually reduce the voltage, because then, the power consumptions would be significantly dropped. But then since you're kind of like in the border that if you go a little bit more, then you start flipping bits and creating errors, you give the opportunity for the attacker. So before, the guard was too high, so you cannot really undervolt and create flips. But the researcher at Intel said, okay, there is the opportunity for reducing the voltage a little bit more, and this way we can actually save a lot of energy. And they did that, but then the adversary said, oh, okay, now I have very tiny guard that if I reduce the voltage a little bit more, I can actually flip it. And that's what they did. They reduced that. And then on top of that, since they kind of, offload the power management to the operating system, then it's kind of like the attack set results that opens up. The operating system can be compromised. The attacker can change the voltage. Now the voltage guard is so small that now you can actually flip bits, and then you can do lots of things with it. So the paper basically talks about all these possibilities of changing things in the multiplication, changing things in the encryption, and all those things. So you can just, you have this tool that you can flip bits, then you can basically, apply to many different things. Yeah, specifically, you can apply to SGX, for example, but you can apply to any other things as well.
How does the attacker change the voltage?
So the voltage is supervised by the operating system. It's starting I think the Hazel generation or Broadwell generation. It's kind of like they call it usually governors. So it's like they have different states, and each state has certain voltage and certain frequency. So think about it like 16 or 20 different states, and each state has different voltage. And the operating system, depending on the workload, decides which state to work on. The assumption is that these states are decided correctly to answer the workload, to keep up with the workload. But the malicious operating system can intentionally choose a wrong state, which has a lower voltage or lower frequency, or higher voltage or high frequency, whatever that creates a difference, and apply that to the system. Okay. Yeah. Right, guys.
Okay, my name is Christopher Reed.
Lisa, and this is Sanctuary Arming Trustum with Research Space Enclave.
So top and right is a problem. So the traditional design used by ARM Trust Zone only separates the execution road into two roads, the normal road and the secure road. And both of them sit on top of the trusted firmware. And we trust the secure road, but we don't trust the normal road because the normal road is running a traditional OS and has a really large attack surface. But now the problem is, because all the secure apps, all your like sensitive apps, run inside the secure road, the more secure apps you have, the larger the attack surface becomes. So if there's a malicious secure app or an insecure implementation, that could compromise secure app and in turn compromise the whole trusted OS. So the larger attack surface is the problem, and due to this, it kind of limits the capability of the developers to load in like custom secure apps into the secure world because it causes a lot of vulnerabilities. So a little bit of background on their solution is there's a device called Trust Zone Address Space Controller inside ARM processors, which basically can restrict or filter memory accesses based on bus IDs. And bus IDs are given to any devices, bus controllers that could access, do memory accesses.
So the dread model is that the adversary can compromise normal one, world applications and even run them. But the adversary cannot compromise the trust zone. So what they try to do is assuming that we're gonna be only running the minimum vendor code so that the chance of the vendor codes that are being already compromised is very low. And then we are getting rid of the option that they can physically alter the hardware.
So the basic overview of the solution is to create this tertiary. So other than like the secure road, there's going to be a road called Sanctuary, which is actually going to run on top of the normal road, but it's going to be its own like compartment with its dedicated resources and a two-way isolation. So any secure app is going to only have its own instance of secure library, and only its instance of core, and it's not on the diagram here, but like its own part of the memory. And those resources are not going to be shared with anyone else. I know the graphic, but it's roll of tanks. I don't play it myself. I couldn't find the version without roll of tanks. But like usually you don't want that to happen. But for Sanctuary, well, it's saying you want that to happen. You want your core to be like dedicated. So to go through how Sanctuary is like built, because this is kind of an important part that the paper goes through, is first of all, the normal app, if it wants to use a sensitive service, it makes a call to a kernel manager asking to create a Sanctuary instance. So the kernel manager goes ahead and separates off a core from the current OS. And once it does that, it hands over the control to the static trusted app, which is basically an app running as part of the vendor code inside the secure road. Once that happens, the Sanctuary library is loaded into the Sanctuary instance. But before it does that, the static trusted app has to verify the integrity of Sanctuary library because you don't want that Sanctuary library to be modified by anyone else. So the Sanctuary library signature is checked against the signature that the vendor code has to guarantee that the Sanctuary library has been unmodified. Actually, I should have also said, sorry, going back, but also before the Sanctuary library is loaded in, the static trusted app makes sure that every content in the core, the cache and the dedicated part of the memory is wiped. Now, once that happens, we can load the secure app, but just like the case of Sanctuary library, it has to verify the integrity of the secure app. So it has to check over the hash that is computed over the binary of the secure app to ensure that the secure app hasn't been modified. So that's also another signature checking. And it also does support remote attestation, just like how ARM Trust Zone does through the vendor code. So it's just using the services that was already provided by ARM. So again, like that's kind of what you want here. You want those docs to have like dedicated access to their plates and not anywhere else, just if it's a Sanctuary instance. Yeah, and just going over, this is an extension of the background part. Just going over how like this isolation is achieved is each of the cores here are gonna be given different bus IDs, so bus 0, bus 1, and bus 2. And the trust zone address space controller can basically tag each memory accesses or tag memory accesses and limit their accesses based on those tags. So core 2 is gonna have dedicated access to this part of memory, and core 2 is probably is gonna be that core that's running the Sentry instance. But core 0 and core 1 is gonna only be able to access this part, and the accesses cannot cross in both directions. So core 2 cannot access the normal world or the secure world, and core 0 and core 1 cannot access the Sanctuary memory. The shutdown of Sanctuary is also kind of an important part. The normal signal shutdown, meaning it's done with the secure services, but so the secure output exit and save its state as a sealing service. The sealing service was kind of discussed in the class as well. It basically uses a hash computed over the binary of the secure app to save any state. And using that hash is important because that means if the binary is modified, then the hash is going to be different. So in case a malicious secure app was like a modified secure app was loaded in, because the hash is different, it's not going to be able to access any previous states. Then Sanctuary library zeroes out all the CPU cache, which is important so that there's no any like remaining data inside the CPU cache that may actually leak information about the secure or like sensitive services. And the Sanctuary library signal static trusted app that it's done doing that. And the static trusted app unlocks the CPU core memory, zeroes out all the shared memory, and returns those to the normal world and the secure world. So.
Yeah, so additionally on top of that, the best part of the Sanctuary is that it can still communicate with the normal world, which is unsecure, and then the secure world as well. So how they work is that they don't share memory, but they can still communicate. And so the Sanctuary usually can request things, and then they'll receive whatever is given by the application that is run on either side of the normal or secure world. And the best, and one of the parts of the Sanctuary app always runs in the EL0, which is the lowest privilege. So it won't be able to access any other parts of the data. And you can use L2 cache or not. Using L2 cache is still protected against direct access of the memory. However, it is vulnerable to side channel leakage. However, if they don't use L2 cache, then no side channel leakage is possible.
Yeah, that's because L2 cache is a shared cache between the CPU cores.
And the evaluation, for evaluation, they use the HiKey 960 ARMv8 model, and this has 4 cores. And again, the data gathered on this board is going to be mainly divided into with or without the L2 access. So first of all, they cared about the kind of the delay that the Sanctuary provides and the causes. So what's actually important is that the L2 represents Sanctuary's access to L2 shared cache, and here the regular, so here, legacy application is referring to the non-secure application, and TA is referring to the trusted application that's running the trusted world, and the SA is the Sanctuary application. And the time it takes for the regular application to call the trusted application is comparable to the original legacy application's time to call Sanctuary app. So there's no performance difference between calling the traditional trusted app versus the Sanctuary app. Then the setup performance. So in the worst case, the setup takes about 450 milliseconds. And here you can tell that the core related task is what usually takes the most amount of time. So like, let's say the shutdown core or early core initialization, and then the setup kernel space. So those are what usually takes a while. And that's where the L2 cache really shines. If you utilize it, it costs a lot of time. And same, but for the tear down, which is breaking down the Sanctuary, when you're done with the Sanctuary application, they actually have similar performance with or without the L2. And this is actually when they completely restart the core and wipe everything that is on the specific core. And here the total setup time and tear down is less than 600 milliseconds. And with L2 cache, it's only 340 milliseconds. So we're going to talk about a use case evaluation. The research actually wanted to create a one-time password for two-factor authentication. There's 2 main parts to it. You can kind of see it more as a provisional secret key generation part, and then the second part is actually generating the one-time password. And what's important is that Sanctuary app utilizes its own application, but also use parts of other drivers and other functions that are within the OPT, which is the trusted world. So when the legacy application or whatever program you run asks for a secret key generation, then the Sanctuary app will be made, and then it will refer to the trusted world, which in the trusted world, because they have a trusted hardware, it is able to generate a secret key here called KTOTP, which is then sent to the Sanctuary app and then stored again in this trusted world. And when you actually go to generate the one-time password, Sanctuary app will try to retrieve the secret key, the KTOTP, and then utilize the algorithm that it has to make the one-time password. So here again, the provision key, the main thing is the delay to create secret key, and the generate the OTP is delay that the user experiences to until they get the OTP back. And here you can see there is a performance difference with using L2 and without L2, but it's not significant enough for the user to actually experience it. So the interpretation is that the setup, communication, and the breakdown of the Sanctuary is fast enough so that the user does not feel like, oh, this is slowing down the process. And they might be like, oh, this is actually kind of safer and it's still fast enough for me to not have any worry about it. And the two-way isolation reduces the attacker's capability to extract data, which is again amazing. And it opens up more programs to be trusted in a traditional trusted application. So the traditional TA development is expensive. It takes a lot of management overhead, so like a lot of overtime costs, and then from a business perspective as well. And also, as discussed before, the more TAs there are, the more vulnerabilities there to the trust system, and they want to reduce that. And this opens up more security to more general applications.
For the future work, the interesting thing is a similar design has been already implemented by ARM called CCA, Confidential Compute Architecture. Their terminology here is different. Instead of Sanctuary, they use a terminology called RHEL. But this design is actually implemented in our ARM v9. I don't know if they will base their work off of a Sanctuary. That's ARM is a proprietary company, so only they know. But basically, the idea is similar. RHEL is like a thing on top of Trust Zone. It's a step further from Trust Zone, where it creates like an instance of its own for a secure and a sensitive app. So that unlike Trust Zone, where multiple secure apps are sharing resources on top of a single trusted OS, Realm is now going to be in its own isolated compartment. And a little bit different thing about Sanctuary. Sanctuary was trying to use like a existing hardware to get around it, but now this is a design in ARM v9, so it does have some hardware support for more efficient design, more efficient performance. And the discussion points, our discussion points are kind of centered around performance, because that was what the paper was also concerned about, which is is the performance impact acceptable for prolonged use case? Prolonged use case as in not just one-time password, but if the sensitive app has to be used for a longer time. And how the performance impact differ if we need multiple Sanctuary instances? This is something that the paper didn't really go through in its evaluation. And
the last one is it's a trade-off of vulnerability, side channel effects, with the performance benefit of the utilizing OT cache.
All right, thank you guys. Great. To talk about the last discussion points very soon, but it's a very good point. And yeah, it's kind of like, so next group actually can come over here and set up first. The confidential compute kind of fix the issue of performance hit a little bit, because it supports over hardware rather than software, because this way you kind of for executing anything you have to kind of do 2 steps, versus for this confidential, for the CCA structure, you at least do things over hardware, so it's much more faster. But yeah, generally that's it. Can you maybe, you can actually join over Zoom and then. Professor. Yeah.
I have a question about that paper.
Sure.
So I was reading it yesterday and I noticed that they didn't really do any actual evaluation of the security of Sanctuary. Mostly like their evaluations all focused on like performance and stuff. Is that because it's like, given the measures that they implemented, is it just like assumed that it's all like secure in practice, or is there any other like actual research done on how secure the Sanctuary implementation actually is?
So the part that it's secure or not really requires some formal verification, really. So they kind of, so two things, right? There are some assumptions that they say that, okay, we are assuming this, and this is the threat model. And they're saying that, okay, we are designing our system to follow this assumptions. And whether this assumption is correct or not, that's something you can investigate. But whether their actual implementation is correct or not, or maybe buggy, that's something that's unfortunately is not easy to verify. And that's the same issue with CCA, same issue with SGX and so on. So that part, nobody knows. I mean, the fact that you can open source things and people can start playing with it and see it, that's actually the way to move forward and actually being able to verify that part of the problem. But the assumption part is basically what people can read and verify. Does that answer your question? Yeah, go ahead, guys. You start sharing. I'm recording. Yeah, go ahead.
Hey, I'm Sid, and we researched the paper Occupancy, which is a privacy preserved remote deep learning interface, and it's built upon the SGX framework. So let's start with discussing the problem. So basically, cloud-driven deep learning is kind of everywhere in the one world. Chances are, if you're using an app, then the app is somehow interfacing with some sort of cloud-driven deep learning network, hosted probably by a service like AWS or Azure, where it's essentially sending your data, such as like your usage, maybe your voice recordings, and then the deep learning model, which is designed to detect something, spits an inference back, which the app then uses. Obviously, this has many benefits, like because it's hosted on the cloud, we get increased accuracy. And we also get things like, we don't have to worry about device compatibility, for example, but it does come at the cost of serious security concerns because we are exchanging sensitive data over the cloud and networks.
Yeah, so now we're going to look at the privacy and threat model. So in the paper, they outline kind of three main components. So the first is the mobile user, and then the second is the app developer, and then finally the cloud platform itself. So the key thing is that the mobile user is the one that's generating all this user data. And so when they're using these apps, it kind of generates a lot of data from their daily life. And so this data is really sensitive, and so it's important that we protect it. And so the app developers then develop the mechanisms that take the user's data and send it towards the open source DL models that are on the cloud.
The goal of Occupancy is basically to keep everything that's great about cloud-driven deep learning, such as basically the accuracy and the latency and stuff like that, and basically add a layer of security over the data to make it basically protected as opposed to what it is currently, which is very vulnerable. And just to sort of reiterate, we weren't looking to use any sort of discounted or partial model. We wanted to use the whole deep learning model at a minimal trade-off for latency, because obviously we have to recognize that because it is a deep learning, because there is security, but there is going to be some overhead, and it's not going to be fully lossless.
Yeah, and so here's the solution presented by Occupancy, which is basically they find a way to preserve privacy with the SGX enclaves. And so as we've covered in the class, the SGX enclaves basically prevent memory access from even the OS. And so this is really useful in this use case because we can take the input from the mobile device, which is the user's private data, and we can feed it in directly to the protected memory or to the memory inside the enclave. And this goes straight into the DL engine. And afterwards, we can take the result, which is the inference, and feed it directly back to the mobile device. So this also prevents inference result manipulation, which is basically when people try to kind of manipulate the results of being sent back to the mobile device.
Okay, so this concept that we sort of discussed in class seems like a great solution. So, I mean, if Snape doesn't show up and penetrate our minds, then our data should be safe. If Snape just showed up, it looks like our solution is not safe. So the big issue with this is that, like, basically we use too much memory. SGX is limited to a memory size of 128 megabytes. Whereas the deep learning networks these days tend to go up to almost a gigabyte of memory usage. So essentially what we're aiming to do with Optimacy, or what Optimacy, the paper was aiming to do, was optimize on the three main memory usages, which is essentially model weights, intermediate feature maps, convolutional computation. Yeah, and so just this diagram is basically just to sort of indicate that when you don't have enough memory, what ends up happening is that you end up having to swap out the data from the enclave to unprotected memory. And what ends up happening usually is that it kind of makes the enclave redundant because the data is going to be in unprotected memory at some point. So yeah, now we're just going to delve into how the three basic culprits for how we can optimize memory performance. Okay, so the first one is model weights. Basically, we don't actually absolutely have to protect the model weights when we're trying to protect data as a primary concern. So what we do is we store that in an unprotected section. Of course, this does raise the concern that, like, what if, since these are left vulnerable, what if someone comes and attacks the weights and the model is rendered useless? Because of course, like, the deep learning network relies heavily on the accuracy of these weights. So as a solution to that, Optimacy uses a hash checking based on weight modification. If it detects it, then it basically says that something is wrong. And of course, there's the computational bottleneck of copying weights and hash checking. So the way that the paper resolved that is simply by using a parallel pipeline, parallel computation. The second part is intermediate feature maps. So basically, deep learning models rely on these things called feature maps, and for like latency purposes and to optimize on time, you would ideally have these stored in some sort of cache. But because we're trying to optimize on memory and not time, what Optimacy does is that it uses a bunch of smart prediction models, and it pre-analyzes the model essentially to check how often a feature map is used and how many times a feature map is used. And it'll only load in the feature map that is required for the minimum duration. So we're using as little memory as possible. And yeah, so basically I just addressed that. What if the same feature map is used multiple times at various points in the deep learning model? And the way it fixes that is it just analyzes the model and it determines how many times the feature map is used. And once that preset number of times is achieved, the feature map is then deallocated from memory. And this diagram just shows to illustrate that. So partition convolution, essentially convolutional operations take a lot of time, but what we do is we use a process called convolutional lowering to sort of speed this up and decrease latency. Unfortunately, this in turn causes a memory overhead, which the paper then reduces by using like a fairly common strategy. It divides big jobs into smaller operations, and that reduces the memory consumption by essentially a factor of how many partitions you make in the job. Okay.
Yeah, so now we're going to look at the testing and results. So here's kind of the testing methodology that was used. So they wanted to answer kind of three main components. So first, they wanted to figure out whether the DNNs would actually fit within the SGX's memory limits. So this is to avoid the heavy overhead that's incurred with paging when you don't do this. And they also want to evaluate whether it would have good latency with the inferences, and also whether the memory usage would be acceptable. And the last thing that they needed to measure was whether there would be a noticeable energy like saving in the smartphones. So this is to see if there's kind of a practical benefit for this approach. And here's kind of the experimental setup that they used. So they used Linux machine as kind of the server that's running, and then they had Android devices, and they all ran these kind of common CNN models. And so the important thing to note here is that they use models of varying sizes. So they use models that are almost like 1 gigabyte in size. And so this is just to test whether different sizes will work. And they measured 3 baselines. So they measured the SGX paging, which is basically just the naive approach with just using the deep learning model inside the SGX enclave. They also measured the native model inferencing, which is just inside unprotected memory, just to see the baseline performance. And then lastly, they tested on the mobile devices themselves. So the first question that they answered was, does it fit within the SGX's memory limits? And the answer is it does. So they're running this VGG19 model, which is one of the larger larger models that's commonly used. And they're able to reduce the memory effectively from 980 megabytes to 74 megabytes, which definitely fits. So here's the part about the speed and like the latency. And so they wanted to first compare it to the SGX paging approach. And they found that it's about 3 times faster, which is a significant latency improvement. And compared to the native inferencing, it adds about a 72% overhead, which is acceptable compared to the SGX paging approach that is like 6 times slower. Okay, yeah. So here's the energy consumption. And so basically, you can just see like compared to on every model that they've tested, basically the energy consumption comes out to being anywhere from 2 to 11 times more less energy consumption. And lastly, they're comparing to the devices themselves. So here we can see that it's about double the speed on a Pixel XL kind of device. And they also wanted to test on different network bandwidths to see if occlumency can be used in realistic settings. So they found that across different network settings, it also had a less latency. And the last thing that they needed to test was whether they could, whether it would be resistant to weight corruption attacks, as explained earlier. And so they basically checked with different policies. And so it's important to note that occlumency uses policy 2, which is the weight loading and hash. And so this successfully detects against all the types of weight corruption attacks. And then also they want to test if there were speed improvements with parallelism, and there are. So now we're going to move on to the discussion points and kind of future improvements. So the first thing that was kind of raised towards the end of the paper is about side channel attacks. So they talk about how you can look at the memory access patterns to extract sensitive data from like when the deep learning inferencing is occurring in the enclave. And so this is a future area of improvement for security purposes.
We also thought it would be fun to explore like developing a TEE for GPUs, because we thought that would be useful to maybe apply to video and image processing parts of the DL inferences, which ultimately would lead to a more accurate, more efficient, and just overall better DL inference.
Yeah, and lastly, this paper really focuses on getting inferences from the SGX enclave, but there's still like future areas that could be explored in model training, and it could be possible that this could develop a way to securely train models as well.
So now that we've used occlumency to discipline our minds, we can collectively bid Snape goodbye because our data is safe. Okay, cool. Yeah, that's it.
Thank you.
For the last point, actually GPUs, I mean, T for GPU is also an active area of research. There's actually some papers on that as well, but that's very interesting, the actually area of research. Any questions, anybody? All right. So thank you, everyone. Yeah, thank you.